talk will begin by Max Prasad from Microchip. Max works as a senior application engineer at Microchip Technology. He has over 8 years of experience working with the embedded systems, new product development, and new product introduction. He's been working with the I3C protocol for more than 2 years, and he has helped implement the I3C peripheral on multiple product families at Microchip.
Thank you so much for the introduction, Michele. Hello, everybody. My name is Max Prasad. I am an applications engineer here at Microchip Technology. And today we're going to talk a little bit about out-of-band system management in data center and the computing space. And before I begin, I do want to mention that I'm pretty sure that there are some people who are attending this webinar who are very well versed with system management. So you probably do way more than what I'm going to share here. My hope is that you're able to learn something new about how I3C is being implemented for system management in the computing and data center space. I also understand that there are probably going to be a few people on this call who have never heard of system management, or this is going to be new for you. That's probably mostly because you're either not directly involved in the computing or data center space. And my hope for you guys is that you will learn something new about system management as well. So as we begin, just to give an overall perspective of what system management is, as you can see here on the screen, it is the process of overseeing and maintaining the operational functionality of a computer system. So think about in a computer system, you have a CPU, which is the main processing unit, which is where the actual processing of the data happens. However, to make sure that the entire system is functional, there are many other things that also need to be done. For example, think about device attestation or making sure that the communication is secure. You need to exchange some security keys. Or maybe one of the devices needs the firmware to be updated. Or could be that you want to read some telemetry data from different sensors. You want to know how hard the entire server is, and you want to control the fan speed for all of that. So all of these extra things, they are not necessarily, they're not for actual processing of the data, but they are needed to make sure that the entire system is functional. And that's what system management is, and that's where it comes in. And traditionally, for quite a few decades, I2C and SMBus has been used for system management. And recently, since MIPI has launched the new I3C protocol, which is a step up from I2C, and as more and more I3C capable devices are coming in the market, I3C is very rapidly displacing I2C and SMBus in this specific space. So here's just a big block diagram of, this is an example just to give you a visual representation of how system management would look like. And you can see here, you have the CPU, and then you have the BMC. BMC stands for Baseboard Management Controller. And usually BMC is the chip that's responsible for handling the system management related activities or whatever that needs to be done. And depending on the complexity of your system, you may have one or multiple BMCs as well. And those BMCs can communicate amongst one another as well. And here you can see there are many different devices like root of trust, maybe a couple microcontrollers, temperature sensor, IO expander, serial EEPROM, and then you have some PCIe slots where you have maybe an SSD connected, network interface card, and all of these are interconnected through I3C. And of course, we'll go a little bit more in depth into the individual use case a little bit later in the presentation, but I just wanted to give you a little bit perspective visually of how it would look like. And I also want to cover a topic of in-band versus out-of-band. What you see here on the screen is a solid-state drive, SSD. And typically in an SSD, it has the PCIe port, and the main NVMe controller that's there uses the PCIe port for communication. That's where the high bandwidth data transfer happens. And of course, there's a management endpoint in there as well that can use PCIe for system management. And when it happens through the PCIe port, that's called in-band system management. But then there is a lot of application for out-of-band system management as well. And you can see that it happens through a different port. Used to be SMBus I2C and now I3C port. It's in the same connector, the PCIe connector. So you have the PCIe port, you have the sideband port. And this is where a lot of the system management related activities happen specifically because of the versatility of a two-wire serial communication. So I wanted to give you this perspective because anytime we're connecting to a PCI interface or something, we will most likely be using an out-of-band interface for system management and I3C connections. And when it comes to system management, there are multiple protocols that happen, and there are many different layers, what you see here on the screen. The topmost layer is the application layer, where most system-level applications reside. So whatever application as a firmware or system developer you need, that's where you will write. However, right underneath the application layer, you have the protocol layer. And in the protocol layer is which determines the type of message that's being sent. And I've added 3 examples. PLDM stands for Platform Level Data Model. SPDM stands for Security Protocol Data Model, which is where a lot of secure transactions happen. And then you have NVMe MI, that's the management interface for the NVMe devices and protocol. And the type of message that you use typically is determined by the device that you're talking to. For example, if you're talking to a microcontroller, you will probably be using the PLDM message. But if you're talking to a root of trust device, then you want to make sure that all your transactions are secure. So you'll probably be using an SPDM type of message. And if you're talking to a PCIe solid state drive that's connected through the NVMe interface, then you'll probably be using the NVMe message management interface. So the type of message you choose is dependent on the type of device you're talking to and the platform you're using as well. And the same and the same platform can use multiple types of messages as well. Because, for example, if you take look at the block diagram that I shared earlier, there are different devices connected to the same bus. So you can use different message types to talk to different devices as well. And usually all of these messages are sent using the transport layer. And the protocol that is used over there is called MCTP, which stands for Management Component Transport Protocol. It is very commonly used. And what MCTP basically does is that you got the message from the protocol layer, which is usually a pretty long message. And what MCTP does is that it breaks the message down into individual packets, formats it, and then it transports that packet physically from one endpoint to the other endpoint. And that physical transport happens through the physical layer, which is where I2C and SMBus was being used for the longest time. And now we're seeing I3C being used in that to transport those packets from one device to the other. So let's talk a little bit about MCTP and how the transition from SMBus to I3C looks like. And I do want to mention that I'm not going to go into the details of MCTP protocol itself. The protocol is public. I have added a link at the end of the presentation, so you can actually go take a look and download the public specification and read up on it. I'm going to specifically talk about MCTP's the transport binding spec with I3C. But before that, of course, let's talk about why is there a need to transition from SMBus to I2C? And if any one of you have used I2C before, you know how hard it is to avoid address collisions, because every vendor has their own implementation of addressing. And also ARP, which stands for Address Resolution Protocol. In SMBus, it's defined in SMBus, but not all devices implement it. Which can be a challenge. And one way to overcome that was to introduce like a multiplexer. But because in a multiplex, only one device is connected at a time, which will make sure that there's no address collision. But the biggest problem with the multiplexer is that the switching of the multiplexer is most likely asynchronous to the messages that are being transported. So for example, if the BMC is trying to communicate to this SMBus device, and that message happens to be a really long message that it's sending, it could be possible that the multiplexer just switches away while the transaction is in progress. Or think about maybe the BMC send the message to the SMBus, and this device right here is preparing a response data. And by the time it has the response data ready to send it back, the multiplexer switches away, in which case this device will get a NAC on the bus. So it's not the most intuitive solution, especially when it comes to MCTP, because of long message sizes or long running tasks and everything. And of course, there are other limitations to I2C as well. We know that it is not a true two-wire interface. the data transmission happens through two wires, as we know, but there's always additional lines for interrupts and reset in some cases as well. And just think about it, right? The more number of devices, the more interrupt lines come in as well. Like, for example, temperature sensor. In a server environment, there could be like hundreds of temperature sensors. And if each temperature sensor has an interrupt line, then it becomes problematic. You may need just an additional controller just to handle all the interrupts as well. And different vendors do it differently. And also data rate, right? Yes, I2C can go up to 1 megahertz data transfer, but in most system management applications, the data speed is still limited to 100 kilohertz or 400 kilohertz, which is a limitation. Now, transitioning to I3C, it has a very clear addressing strategy. I think that it's amazing how dynamic addressing is implemented in I3C. Hot join is supported, so hot plugging of devices is supported. And there are certain things called CCCs, which stands for Common Command Codes, which are defined in I3C. And they're all standard for all vendors. So that means that it's not going to change from one vendor to the other vendor. So I think that is one of the biggest advantages. But in addition to that, I3C has replaced the standard multiplexer with a new hub architecture. And this hub architecture that you see right here, it can support both I3C and SMBus devices. And the I3C devices operate in transparent mode. What transparent mode means is that all these I3C devices are connected through the hub, and they appear as if they're logically connected to the same bus. That means that all devices are connected to the BMC and they can talk, just as if they are on the same bus. However, the devices, the upstream and the downstream devices are electrically isolated. And that's a big plus because that electrical isolation can allow voltage translation, means that the upstream devices and downstream devices can operate at different voltage levels. But at the same time, it can allow higher overall bus capacitance as well. Because in I3C, you have 50 picofarad bus capacitance restriction, which I feel is good, but can sometimes be restrictive when you have more devices to be connected. So using a hub can allow you to have, because it's electrically isolated, you can have more overall bus capacitance for the system as well. And for SMBus devices, it uses an agent mode. And what that agent mode simply means is that these transactions are buffered. So these SMBus devices are buffered, so it appears continuous, because one of the requirements for MCTP is that it expects continuous communication between a BMC, between the primary endpoint and a secondary endpoint. So by buffering these transactions for SMBus, it appears that it is continuous. Of course, there is a limit to the buffer as well, but it's better than a multiplexer. And of course, there are other improvements over I3C as well, like in I3C, like it is a true two-wire interface for interrupts and reset. It can go up to 12.5 megahertz in SDR mode. Hopefully, it supports DDR mode as well, double data rate. The bitrate can go up to 25 Mbps. MCTP currently hasn't defined anything for double data rate mode yet, but they have left it open. So maybe in future, something will be included. You never know. So let's talk about the SMBus to I3C transition flow, because we all know that I3C is backward compatible to I2C and everything. But the biggest challenge that came up in this in the field was, how do we make sure that this backward compatibility works out? And at the same time, because as more and more devices are transitioning from SMBus to I3C, chances are that in a specific system, not all devices are supporting I3C yet. And they're being upgraded in a phased manner. So the idea behind this transition flow is think of the basic idea is very simple. The idea is that even if you have at least one SMBus device on the bus is going to operate in SMBus mode. The only way the entire bus will operate in I3C mode is when there are no SMBus devices on the bus. And what you see here is a very simplified transition flow. I do have to mention it is very simplified because there are a lot more steps in there. And I've added a link to the specification where you can access it. It comes from the SNIA specification, or even the PCIe sideband specification has it now. And there are a lot more steps in it. And I tried to simplify it. So this is not exactly how it looks like, but just it's good enough to understand. So the idea is that it will always start in SMBus mode, and then it will send a 7H7E, which is a reserved address for I2C. So all I2C devices or SMBus devices will NAC it, whereas I3C devices will act this. And then it goes into SMBus device discovery to make sure that to check if there are any SMBus devices on the bus. And if it discovers any SMBus devices, then it stays in SMBus mode at 3.3 volts. But if there are no SMBus devices on the bus, it will send another 7H7E and discover I3C devices. And then it transitions into using I3C mode. And it also changes the voltage down to 1.8 volts. So this is how it kind of looks like on the bus. And as you can see, it initially starts in SMBus voltage, and then there is a pull-up change. So after it determines and identifies that there are no SMBus devices on the bus, that's when it turns off the SMBus pull-ups and turns on I3C pull-ups, and you see the voltage transition into a lower 1.8 volts. And that's where all the I3C transaction takes place. And of course, you can always do a reset and then go back to using the SMBus mode and start the bus over again if as the reset process and everything. But that's how it is defined currently. As devices are being upgraded, it could be possible that in a server rack in a BMC or on a backplane, you have the main BMC and certain devices are not yet upgraded to I3C, but you have the new SSDs supporting I3C. So it's important to make sure that the transition flow works pretty well. And now let's discuss some key features for MCTP over I3C. And for initialization and device discovery, a regular hard join and NDAA-based dynamic addressing is used. These are all specified in the I3C specification that you can access. To negotiate transmission sizes, the packet size for each MCTP packet, the negotiation happens using some CCCs that's for maximum read length and maximum write length. So you can use the get set CCCs for max read length, write length to negotiate the packet size of the MCTP transmission as well. And then for data encapsulation, it uses the regular private reads and private writes. So when it is sending from primary to secondary, private write, from secondary to primary, it's private read. It can happen in an interrupt-based environment or a polling-based environment as well. And then there's error detection and handling as well. And so basic I3C has provided certain like CE0 through CE3, that's the controller errors, TE0 through TE6, that's a target error. That's specified in the I3C specification. And MCTP goes beyond that by adding additional CRC8 based packet error correction byte, includes some recommended behaviors to make certain CCCs much more robust, and also has handling mechanisms. So what happens in case one of the devices on the bus just holds the data line low, in which case it also has certain behaviors or mechanisms that you can use to overcome those situations. And what you see here is a device enumeration. So it's like when a secondary device is connected to the block, could be because of hot plugging, or it was powered off, you're turning it on, or initial bus initialization. I'm not going to go into the details here, but just the flow here is very simple. The secondary device will request for hot join. And then when the hot join is acknowledged, the primary will send the NDAA CCC, which is where the dynamic addressing happens. And then it will just send an MCTP request message to verify that the device has been assigned the address and it's there on the bus. So it's pretty straightforward, goes along with how dynamic addressing works in I3C as well. And here's how the packet encapsulation looks like. So you see from when the data is being sent from primary to secondary, you will see that it's a standard private write for an I3C. And what you see here is how an MCTP packet looks like. And I'm not going to go into the details of this packet. You can access the MCTP base specification for details of what this means. But just to know that these bytes are actually just encapsulated as a regular private write command. And then when the secondary device is ready to respond to the primary, it will start, this is an in-band interrupt base, so it will respond by requesting for an in-band interrupt with a very specific mandatory data byte, which is specific to MCTP. And then when the primary receives this in-band interrupt, that's when it will go ahead and start reading. This is a private read command that is initiated by the primary to read the data from the secondary. So it's just pretty straightforward, regular I3C stuff, good stuff. And then this is a big picture view. So each one of these that you see here is an MCTP packet, and each of these packets has a payload. And what happens on the secondary side is that it receives all these packets, it takes the payload and assembles it into a message. And when it is ready to respond back with a message, then it basically splits it into multiple packets, encapsulate it as per MCTP specifications, and then sends it through I3C. And this message type can be anything. Could be SPDM message, could be PLDM message, could be NVMe MI message, could be MCTP control messages, whatever it may be, depending, again, on the type of device you're talking to, the platform and the application. So to end this, I do want to cover certain use cases for I3C based system management. So you understand like how it's currently being used or it's planned to be used in this environment. And I'll go back to this blog diagram that I showed earlier, and we'll pick out specific use case and applications from this blog diagram itself. And this is just a representation, obviously. If you are involved in system management, you probably have your own unique application, which is great. Just know that anywhere you're using I2C SMBus, now it can be upgraded to I3C because the specification allows it, and we have devices that support that as well. So maybe we can begin with a simple root of trust secure boot application, right? You have a real-time root of trust device. So what it basically does is that the firmware that runs on the CPU or the BMC that is stored in a separate flash is transferred through SPI. It monitors it. The way I3C is being used here is for device attestation, for example, to make sure that CPU and the BMC, they want to know that the firmware that's coming is coming from the correct source. So they might need to do some security checks, transfer some security keys, make sure that the communication is secure. So all of that can happen through I3C and uses SPDM typically for these transactions. Another could be like a simple firmware update. For any reason, let's say the same root of trust device notices that its own firmware is corrupted, or maybe it's time for a firmware upgrade for the root of trust device as well. And let's say the firmware is stored somewhere in the solid state drive. So in this case, this device can, if it is a secondary controller on the bus, it can assume the role of an active controller and start to, of course, first authenticate the communication using I3C, SPDM, and then read the encrypted firmware from the SSD and upgrade its firmware as well, right? And this can happen for any of the microcontrollers, any device, right? If you want to upgrade firmware for this device, probably happen the same way. Another is inter-chip communication. We see here a couple microcontrollers here that are doing their own system management because microcontrollers can be very versatile. So they can be used for a lot of applications. And what you see here is this a dedicated I3C communication between microcontrollers to make sure that they're transmitting the data, that they're exchanging data as needed between them. And there's another example here in a solid state drive where the microcontroller that is used to interface with the PCIe port, and all of these are sideband. Like we talked about in-band, out-of-band. So all of these are PCIe ports. So these are all using out-of-band management interface here. And so you have there can be a dedicated I3C bus between the microcontroller interfacing with the PCIe port and the actual NVMe controller on the SSD. And there can be other devices connected too, like an EEPROM or a temperature sensor or other microcontrollers, whatever needed can be connected here as well. But it's just inter-chip dedicated communication. And then just overall microcontroller system management, because microcontrollers are so versatile that and of course, if these microcontrollers are added to the bus for system management, then the BMC needs to talk to these microcontrollers to make sure that it is doing, the microcontrollers are doing what they're supposed to do, right? So that could include sending specific messages, can use a PLDM message or an SPDM message, depending on what kind of message that they're, or at the application that they're using it for. So that's what can be used over there. And then you have solid state drive access. This is again the same thing. BMC is now wanting to access the solid state drive. And a simple example could be that you have the, let's say an SSD is first connected to a server rack. And in that case, typically before the full 12-volt supply is turned on for the actual PCIe data transfer to happen, typically what the BMC would do is it would talk to a PMIC, power management IC, and then just turn on an auxiliary power supply, which is the one that powers the sideband communication, out-of-band communication. So it can first turn on the out-of-band power supply and read certain vital data through the solid state from the solid state drive. Like for example, we call it VPD, vital product data. And it could be like, oh, the capacity of the SSD, the limitations of the SSD speed, whatever, right? And then once it identifies the type of SSD that's connected, then it can turn on the full 12 volt and then do the actual data transfer through PCIe. So this I3C is very useful as an out-of-band sideband communication here. And of course, temperature sensing, right? It's very common for server applications, computing applications, data center applications, to make sure that things don't get too hot. So there's always hundreds and hundreds of temperature sensor in any data center that you can imagine. And I've mentioned it's non-MCTP because in most cases, temperature sensors will respond back with maybe 4, 5, 6 bytes of data. You really don't need like a full MCTP packet encapsulation. So that means that the BMC can just read the data from the temperature sensor directly. And also one of the reasons is that temperature sensors can be a lot. Like there can be a lot of temperature sensors, and so if you're using I2C SMBus to read that data, it can take a while to read data from all of that. So using a high bandwidth I3C communication, reading data from all these sensors, it makes it really fast, makes it very easy as well. And then just overall some final thoughts before I open up for a Q&A session is that system management, it's a key application area in the computing and data center space, and it's also the industry where a lot of high bandwidth data transfer happens, long data transfers happen. And of course, I2C and SMBus has been used because they're easy to use, they're simple, just 2-wire interface. But of course, because of the limitations that we talked about earlier, I3C is rapidly being adopted in this because of high bandwidth, just true 2-wire interface, simplified board layout, power efficiency, and of course, the new I3C hub architecture that we talked about is very helpful. And we have the specifications that support it now. So MCTP specification now supports I3C as the transport binding. That means that anywhere you're using MCTP for system management, and it doesn't matter what your other higher level protocol is, could be PLDM, SPDM, NVMe, MI, or any other message type that you're using. If it is using MCTP, you can now use I3C. And now you have I3C capable devices available in the market that you can use and add to your next future designs as well. So that is that. And then if you're looking for a light weekend reading, then I've included all the specifications that we have talked about. Most of these specifications are public. I think maybe the SNIA or PCI specifications may require your organization to be a member, but outside of that, enjoy your weekend reading of all these specifications that we talked about. And also, there are some great educational resources out there. In fact, there is a great podcast that just released today from Microchip on how I3C is being used in data centers, and it's a great read. Definitely listen to it. And then there are many other resources that are available on MIPI as well. There's a video on I3C, many articles available out there, blogs, white papers. So definitely highly recommend go to MIPI website, and you'll find a lot of other educational resources. But that is all I had for now. And then I can wait for Michele to come back up. So we can maybe get into a Q&A session.
In slide 16, which I don't remember offhand at this point, is there a specific reason it's shown communication between primary BMC and secondary MCTP device controller instead of primary controller target device? Is there any use case where MCTP device can become an active controller? I don't.
Let me go to slide 16. If I go back to slide 16.
We can read again. The question is rather long, and maybe we should read it again.
This one. Is a specific reason it's shown communication between. I don't know. I don't mention a BMC here, so probably it's a different slide. Yeah. But
Okay.
let me try to understand the question. So communication between BMC and a secondary instead of a primary controller
Oh,
target device. Is there any use case where MCTP device can become an active controller? One of the use cases, like I mentioned earlier, was for firmware updates, for example, right? So if I think it was this application right here, if this root of trust device, for example, needs to update its firmware, then and it wants to read the data from, let's say, the solid state drive, in which case this is a secondary controller on the device by default because BMC is the primary controller. But then momentarily it can become an active controller, so it can drive the clocks and read the data from the PCIe SSD right here. But again, it can be application specific as well. The answer is yes, it can become an active controller on the bus. It depends on which application that you are targeting. But usually the BMC is going to be the main controller on the bus, and it can hand over the controller responsibilities to another device momentarily for other applications, and then it can you can hand it back to the BMC.
yeah. I suspect the question is related to the fact, primary, secondary, but in reality, I think what happens on the first segment, the BMC is the controller, and I hand it over to the target, to the hub, who then becomes secondary controller to manage to go on the PCIe device. Yeah. So in that sense, yeah, that's clear. Okay. Maybe I have just some questions here. You mentioned, that it's beneficial to have the HDR, high speed modes. In this implementation, were you able to use any of the HDR, for example, like the DDR, which is available under the I3C basic, or the standard data rate was good enough for what you had to do?
Right. So right now, as per the MCTP I3C specification, they haven't defined anything for any of the high data rate modes yet. They have left it open to vendors to implement it in their own way if something that's needed. But the basic transport specification is all standard SDR mode right now, because that's where most devices are supporting as of now. So they wanted to make sure that there's devices available and everything. But however, there is maybe it can be added later on. I just want to mention that as of right now, the specification doesn't have anything. Everything in the specification uses the regular standard single data rate SDR mode for I3C. Maybe in future they will upgrade it and add some HDR modes, but right now there are none.
Well, I guess you're also going from the standard I2C based to the standard data rate. You already did an 11-fold jump in speed. So I think there is room to grow. Yeah. I think there was a question from the audience if the I3 sessions have been recorded. Yes, they have been recorded. They will be available in very few days on the MIPI channel. Okay. I just out of curiosity, are you able also to manage power supplies to the system management? It was not in the use case you showed. Is that something that can be done as well?
Yes, it can be done. Yes. So you can add a PMIC, like power management IC, on the bus, and then that can be there. Of course, you want to make sure that the PMIC you're adding supports I3C. And then as long as it supports I3C, then yes, whatever functionality that it can do. Yes, but PMIC is definitely one of the big things. I should have included it. I don't know why I didn't include it. But yes. Yeah.
I think you give the idea that you're able to talk to many devices. Also, another question we had on how there are some CCC command to set the maximum packet length. You can query what the target is capable of doing, and then you can actually set them using the set MRL and MWL. Could you elaborate a little bit on how this is done for to negotiate, the packet MCTP packet sizes?
Yes, definitely. So just to give a little bit background, like in SMBus, right, in MCTP, usually when the packets are sent, then in SMBus, it would send the address, the physical address of the device, and then it will send the number of bytes that's included in the packet. And so that means that the receiving device doesn't have any control of how many packets it's going to receive or something, because it's just receiving that data. In I3C, they used a set and get max read length, write length CCCs, and the way the primary host device does is that it sets well, as per MCTP specification, the minimum max read length, write length packet size for an MCTP 64 bytes. So that means that if they want to send longer, then the main host device can send like a set command with set MRL, set MWL with a bigger packet size. Let's say, for example, 128. And then it will wait for some time, and then it will read back using a get MRL, get MWL to read back the data, that whether it was written or not, right? And if it reads back the data that it wrote, that means that the target on the other side has accepted it. But if it reads back a different data, that means the target did not accept it. So in this case, the secondary endpoint has a choice to, when it receives the data from set set MRL MWL, it will then check whether the data that it has received, it can support, with its internal buffers and everything. And if it can support, it will take it. If it cannot support, then it will reject it, and it can, change its return a value that it can support. So that's how the our negotiation happens in the beginning, and it only happens at the beginning when the bus is being initialized. And once it is initialized and the transmission sizes are negotiated, that will be used for the rest of the transaction.
Great. Okay, thank you. You mentioned that you can actually access the SSD, the solid state drive. I'm assuming that you can read, but you could also write. Is that correct?
Yes. So yes, from this microcontroller. Yes. So depending on which commands you are sending. So in the way MCTP works is that you send a request packet and then you get a response packet back. So usually the request packet is a private write. So the host device, the primary device, writes to the secondary device, and then and it's usually a message, and then the secondary has to then decipher the message, understand what that message means, do whatever it has to do, and then it will respond back with a response message that is again a private transaction as well.
Yeah. But being a quite delicate, sensitive type thing, writing or reading data from a solid state disk, is there any provision for security, to avoid rogue access? Is there a possibility to use the security layer in the SPDM?
Yes, definitely. SPDM can be used, and it's the same transaction between, let's say, a root of trust device and a BMC or a microcontroller. So if when you use SPDM messaging, right, then there are defined security protocols in there that can be used to either send encrypted data on the bus, or if you're not sending encrypted data on the bus, then making sure that you have verified the device's signature, right, security signature and everything, in one way or the other. And that verification we have seen it happen in two ways. One is that the verification can happen, like the root of trust device, for example, in this case, can verify the security for MCU, this one right here. Or the other one we have seen is that this NVMe controller verifies this, and it is the responsibility of this controller to make sure that this is secure. So then in that case, you don't need it on the other side. So it depends on the application specific, how it is being done. And I have to check like what the standards specify. I haven't looked into detail of what the actual NVMe standard specifies for that. But we can definitely implement secure transactions.
Okay. I think we have time from just a very last question. If you could elaborate a little more, I think you sort of showed this already, but perhaps elaborate a little more on how basically the exchange between, let's say the primary and then the target, not using the IBI, how the mechanism for the response from the target works.
Yes. So in the case of an
For
in-band
MCTP, I mean, of course,
MCTP,
for
yeah,
MCTP
yeah, yeah.
target, yeah.
So if we go back to this case here, right? So in case of an in-band interrupt, the secondary responds back with an interrupt, and then uh, uh, but in case when there is no interrupts, then in that case we will have to poll. So the primary device has to poll the secondary device, and the polling can happen in two ways. One is that it can first do like there's a CCC called get status. So when you do a get status CCC, then usually the data that is returned has something called pending interrupts. So when the device is ready to has the response data ready, it can just set one of those pending interrupt bits. So that way, when the primary reads the get CCC and polls the status, then it knows that, oh, it has a data ready. So now it can do a private read. Or the other way is that it can just skip the get status and just do a private read directly. And if the secondary endpoint doesn't has the data ready, it will nag. So basically, the primary will try again and again. So it will continue getting nags until the data is sent back.
Yeah. So I'm assuming when you have a lot of peripherals, you can have a more orderly, let's say, readout. Instead, if you have a few peripherals, it's better to rely on interrupt. It's more efficient. Okay, great.
Yes.
So I think we are at the top of the 45 minutes of the webinar. I think it was a great webinar. It's really good to see I3C used in such important use case. Actually, it's more than use case. It's really, it's important market. And yeah, MIPI, I think I can express on behalf of the MIPI team that we are really pleased to see this happening. And I also would like to thank people that attended